Hi everyone, welcome to this video where we will see the finite element analysis of a pin jointed truss model. And the purpose of this exercise is to correlate the hand calculations for calculating the member forces in a pin jointed truss with those of the results obtained from the finite element software Midas Civil. So today we'll be taking up this example of the truss, which has some inclined members, some diagonal members, and 2-point loads have been applied at the joints C and F, horizontal force of 6 kilonewton and a vertical force of 21 kilonewton at point C. All the angles for the diagonals, they are 45 degrees with the horizontal chord, and all the joints on this in this truss are pinned, which is normally what we assume for any truss analysis for even the hand calculations. The total height of this truss is 3 meters and it has got 3 bays at 4-meter intervals. So the total length of this truss, you can call it a truss bridge, is 12 meters, and the truss is basically simply supported, so pinned at end A and a roller at end C. The objective of this exercise is to calculate the forces in the members FD, which is this one, and FE here, and FG over here, and finally CE, that is this member. So we need to determine whether the forces that we calculate over at these members are tensile or compressive in nature, and also determine what are the reactions at points A and G. So let's see how to model this particular structure in Midas Civil. So here again I have the blank blank screen of Midas Civil. To start a new project, we go to File and click on New Project. So here the blank model view can be seen, and now we set the analysis mode to 2D or 3D, whatever it is. So we are going to do a two-dimensional analysis for the truss. So we select structure, structure type, and select XZ plane. So Z being the vertical and X being the horizontal axis. So click OK, and just for checking whether the views have been correctly selected or not, we can display the viewpoint. So use the display option here and select viewpoint and click OK. So that's the viewpoint over here on the right side. You can see Z, X and Y. That's the isometric view for now, and if I click on this button here, that's the top view, the front view. So this is the view we will be working on, that is the XZ plane. So the unit systems for the modeling process, the unit system should be kilonewton meters. So we select kilonewton meters from the status bar at the bottom of the screen. We can also select units from tools, unit systems, select kilonewtons meters and click OK. So once the correct units are set up, we can start modeling the truss. Let's see what are the dimensions. Okay, so first what we will do is we'll start by modeling this particular bottom chord here, this beam, and then we'll start modeling the other elements, other members. So we have a bottom chord of 12 meters length with 3 intervals at 4 meters. So let's model that one first. So we go to node element, we go to structure, select base structure, select beam, and we create a beam 3 at 4.0 meters. So that's 3 times 4 meters, add, and we can select just keep it as material 1 in section 1, just like we did for our tutorial 1 for the statically determinate beams. We can initialize the materials and sections with some default value. So by default we normally keep it as 1 and click OK. that is the that is the beam here modeled. Now we can quickly define some material and section for this beam. So I go to properties, material properties, add, and select user define, and enter the modulus of elasticity, say 2 into 10 to the power 8. The materials and sections doesn't they don't matter for the calculation of reactions and forces as long as the structure is statically determinate. Um, for the deflections, yes, we need to enter the correct materials and sections, but for this example we are not concerned with deflection or with stresses, for instance. So we can go for any material or section, doesn't matter. So you can define any material or section here. We are only interested in the forces, so we name it a material, click OK, close this, and we go to section properties now, add, and I'll just enter a rectangular section, name it section, user defined, 0.5 meters by 0.5 meters, and click OK. So there you go, you have the section shape displayed on the screen. Now let us start by defining some other elements. So before I do that, I will display the node numbers so it's easier to refer them when I'm creating the other elements. Let's see what lengths do we have to enter. So first we will start by entering member AB. So member AB is inclined at 45 degrees to member AC, and the height is 2 meters, so that means the horizontal distance from A to B is also 2 meters. So I'll just enter that. So for creating an element out of a given point, a given node, we use the option of extrude. So we select node element and we select extrude elements. We use the selection icon here, select single, click on this node to select the node number 1. You can see the number displayed here, that means it has been selected. Make sure the type is node to line, so we are creating a line out of a node, and enter the distances dx as 2 meters and dz as 2 meters, x being the horizontal, z being the vertical. Okay, and click apply. So you've created one element here. Then the next one is BD. BD is 1 meter vertically upwards from point B, and it's 4 meters from horizontally from the point B. So we enter that here. So use the select single option again. Select node number 5. Make sure it's displayed here. That means it's selected. dx we enter as 4, and dz vertical enter as 1, and click apply. Okay. Similarly, we select this particular node, and this time we enter dx4, dz as -1 because we want to move it downwards here. Click apply, and again select node number 7, and this time you can directly press, so click on this particular box, directly click on node number 7 and node number 4. An arrow will appear which will measure the distance basically for you, and you can click apply. So that's applied now. For the elements, for the internal members, we can simply use the create elements option. So we go to create elements, and we start by clicking on this box first and then snapping on node number 5, 2, then 2 and 6, and 6 and 3. So just click and click to connect to different nodes and create the elements. And once you have done that, you can close it. So here you have the whole truss member generated. So just for clarity purpose, I will change it to a line view. So change it to the line model. Okay. Now we will define the support conditions. We have two supports, pinned and a roller support here. So we go to boundaries, define supports, use the select single option, select this node number 1 first, and select dx and dz, which is basically a pinned support which restrains motion in the x direction and in the z direction, but it allows rotation, so no rotational restraint has been ticked. So click apply. So one support has been applied. Now we select the second one, the node number 4, click on this node and remove dx because horizontal motion will be applied here, and we want to consider only vertical restraint, and click apply. So we have defined the two support conditions. Close this dialog box, go to the works tree, and you will find that all the information has been entered here. You can modify anything. If you want to modify the support, you can just right click on the support type, go to properties, and you can modify them. You can also double click on an entity in the works tree. So if I double click on section, then it identifies on the main model or selects on the main model whatever elements that have been assigned with this particular section ID. So I unselect everything now. Now let us apply the loads. So for applying the loads, we first have to create load cases or create some names for identifying those loads. So we go to loads, we select static load cases, and we give a name, say P. We have point loads on the structure, so I'm just naming it P. I'll just save this model. Type is user defined, add, and close this. Now we go to nodal loads because we have to apply point loads, so which are basically nodes. So nodal loads, and the first load is a vertical load of 21 kilonewton downwards at point C. So I'll select using the select single option here. Click on the node 2 to see the selection. You can see that node 2 has been selected. Select FZ, enter minus 21, minus because it's in the downward direction, and click apply. Then we select node number 7. So we can either create a window like this to select, or we can just click on the node 7. And for the node 7, we want a horizontal force of 6 kilonewton from left to right. So we will make Fz 0, and we'll enter in the Fx 6 kilonewton and press apply. So we've got a arrow pointing in the x direction. And now I'll close this box. So we have applied all the loads and boundaries on our structure. Now before analyzing this structure, we need to do one more thing. The title of this exercise was pin jointed truss, so which means every joint in the structure is pinned. But right now in our model, we don't have such a situation. We have all the joints which are actually rigid joints, so they are connected to them as fully fixed connections. So we need to create pin joints which don't allow moments to develop at these joints. So we need to pin them all. So what we do for that purpose is we create a boundary condition which is basically a release, a beam end release, and we select all these elements. So use the option of select all to highlight all of them, and select pinned here in the beam end release. So pin will basically create pin joints at both ends of a member. So all these members will have both their ends pinned, and then click apply. and close this dialog box. So now you can see there are some yellow dots appearing here, which denote the pin connection. Now this you should be very careful while applying the pin joints, because if by chance you applied the loads on the structure which create some kind of moments at the joints, then you will lead the pin joints will lead the structure to instability, and your analysis will fail. You will have very high abnormal deflections. But in our case, all the loads have been applied on the joints directly, so there should not be any moment. Plus we have a simply supported connection, and this model is a 2D determinate structure, so we can run the analysis. You go to analysis, perform analysis. The analysis is complete. In the message window you will find warning messages. This is because we have used pin connection at all the joints, so it's giving us a warning that it can fail if there is any rotation. You will find that all the warnings point towards the rotational degrees of freedom. So if there is any rotation on the joint, then the structure might fail and you will get abnormal results. But we can ignore these warnings in our case and see the results, because we don't have any rotational we don't expect any rotation to occur at the joints. So go to results now and look at the reactions first. So reaction forces, select the load case P, select values and click on this box here, enter number of decimal points as 2, click OK, and you will find the reactions at the two supports. So vertical reactions at the pin support is 13 kilonewtons, vertical reaction at the roller support is 8 kilonewtons, and you have the horizontal reaction at the pin support as 6 kilonewton. Then we will check the forces. So we want to determine the member forces on the right side of the structure, and we want to determine whether they are tensile or compressive. So we go to forces and select beam diagrams. You can also select from here. You can select forces and select beam diagrams. Okay, now for the compression or tension force, we have to display the axial force diagram. So how to know which component of the force we are looking at? For that we have a coordinate system which is called the local axis system. So all the element forces, they are basically displayed along their local axis. To see what is the local axis system for a given element, we can click on display here and go to element and select local axis and click OK. So it shows you the different colors for the axis, the red being the x-axis, which is the longitudinal axis for a given element. The axial force will act along this axis, so any kind of tension or compression force will act along the x-axis of a given element. So we need to select fx to see the results for axial forces. So select fx here. Display options, you can select exact, and you can click on values, select the number of decimal points as 2 and click OK. So this displays the axial force on each member. I will remove the local axis from the display so that it's more clear. So I go to display again and uncheck local axis, click OK, and you can see the member forces for each member. So we have got some values in positive and some are in negative. So these denote tension and compression. The positive values are compression, the negative ones are the tension values. So this is how you can determine whether the member is in tension or compression. So if I go to um, the PDF file, we can compare these results with the hand calculations. Okay, so first of all, just giving you a brief overview of how the results were calculated by hand. For the reactions, it's simple since it's a statically determinate structure. We have three unknowns at the two supports, and we just solve them by taking moments about each support, taking the um, total summation of vertical forces as 0 and total summation of horizontal forces as 0, and thus we get the three reactions. For the member forces, we use the method of sections by cutting a section along the truss and any part of the truss and resolving the different forces in x and y direction, and taking the equilibrium um, of the moments of vertical and horizontal forces in that section. Also, we employ the method of joints at certain locations. So at a joint, the total force summation should be in equilibrium. So using that summation of using the method of joints, we calculate the results at a particular joint. And then finally we have the results. So we get the results with theoretical results and the Midas civil results at different members, and they are exactly same. So the assumptions made by us in the modeling process are correct, and we are also getting the same type of force like compression and tension. So this concludes this session, and for more examples on other frame analysis and other types of analysis on Midas finite element packages, stay tuned to our Midas UK YouTube page. And that's it for now. Thank you.